Yeah. So let's talk with EEPROM device. So generally how these EEPROMs are available in the market and what way these EEPROM devices you can interface with controller families. Okay. So coming to these EEPROM devices which are working with this Atmel family, and the series for these EEPROM devices which would be AT24C The last two digits represents the value of memory content from this device. Suppose if I am talking AT24C02 and the devices which are available like this 24C32, 24C48. So that means the last two digits which are representing the memory quantity of this EEPROM device. So this EEPROM device, that means suppose if I am taking 24C32, so coming to the memory organization of this AT24C32 device, so which is available here inside 32 kilobits of memory. So that means what is the meaning of this 32 kilobits of memory from this EEPROM device? So this 32 kilobits means, so generally 1K equals to 1024 bits, right? So if I am telling 32K, so 32 into 1024. So I think almost you people will get like 8402. So this is the total quantity of bits, which is 32768 bits available from this device. And already you people knows that, so for 1 byte how many bits? It should be 8 bits. Whenever you are looking to divide, so suppose if you want to tell this number of locations are available from this device, so just you have to divide this thing with your 8, then you will get 4096 bytes. So that means, so coming to this memory organization of this AT24C02 device, so how many locations are available from this device? Total 4096 bytes. So these memory calculations required whenever the people are giving this series. Okay. So now for this AT24C32 device, how many locations are available from this EEPROM device? 4096 bytes. That means this is the internal memory construction for your device. So once you start with 0, then what is the last location? This is the decimal representation. So that means total 4096. Once you start with 0, always the memory addresses starts with 0. Okay. So once it is 0, then what is the last location here? 4095. So this is the decimal representation for your device. So totally which are providing 4096 locations for you. 0 to 4095 is the total decimal representation of memory addresses. Suppose if you want to tell the same thing in hexadecimal form, then you can write 000H2. So just you have to convert this 4095 to hexadecimal. Then how can you convert into hexadecimal? By dividing with 16. So then obviously this is 255, which is F, and 1, and again 5, and F, so which is F. So 0 triple FH. So this is the hexadecimal representation of memory locations, and this is the decimal representation of memory locations. Okay. So that means for this AT24C32 device, how many memory locations are available in the device? So which is total 4096, and this 4096 calculation for be 002 0 triple FH. Okay. Now you people can use this total 4096 bytes of memory for your data storage. Okay. So now if you want to do some operations on this EEPROM device, so you people have to follow this I2C communication with this controller families. Okay. So now let's see the EEPROM devices pin diagram. Like if you want to see the complete pins and what is the way you people can work with this EEPROM device. So which is a simple 8-pin device. And from this EEPROM device, the pins are A0, A1, A2 and ground, and SDA, SCL, and write protect and VCC. So this is the simple 8-pin device which is for your AT24C32 device. So these are the complete 4 pins, A0, A1, A2, A3. These are the 3 hardware address lines, and 4th pin is the device ground, and 5 and 6 are 2 I2C lines which are used for I2C communication, and 7th pin is write protect, and 8th pin is your VCC. Okay, so this device you can tell because it is I2C device. How you people can finalize it is which is I2C device, because you people will find the 2 physical lines from the pin diagram of this AT24C32 device which is having SDA and SCL, right? So if the 2 physical lines are available from this device, it's itself which is a I2C device. Suppose you people are not finding these 2 lines from this device, which will not a I2C device, okay? So which doesn't support I2C communication with the families. Okay, now if you are looking to interface this EEPROM device with the controller, then you people have to connect which pins you have to connect with the controller, and which pins you have to go for VCC and ground connections, and which pin you have to left. So coming to this interface of this device with your controller families, so then you people have to use the 2 I2C lines. Suppose this is your microcontroller which is not support on chip I2C. Okay, so from this microcontroller, so our consideration should be any 2 IO lines I am going to make it as SD and SCL lines, and always these I2C devices which are having 2 lines SD and SCL which are open drain. So open drain means whenever you want to make as a normal pins, you people need this pull-up resistance. So which should be from 2 kilo ohm to 10 kilo ohm. So now I am connecting 4.7 kilo ohm pull-up resistance for this. It should be 5 volts, and this pull-up resistance, after pull-up resistance connection, just I am making with this normal IO lines. Okay, so this way you people have to go through this connectivity of these I2C lines with your device. And what about the remaining lines? Like, so 1, 2, 3, these are the 3 hardware address lines. So because from the unique slave address of EEPROM device, so these 3 pins are the 3 hardware address lines. As a programmer or as a user of this device, you people can go through this connection either VCC or ground. So that's your choice. Okay, but these 3 lines logics, or these 3 lines hardware connection which will decide the logic of these particular pins. If you are connecting to ground, then the logic you can assign in the slave address as 3 zeros, and whenever you are connecting these 3 pins for VCC, you can assign the address of this EEPROM device as 1s. Okay, and this write protect pin you people can make it touch left. So, and you have to connect this VCC line to 5 volts DC. So this is a simple hardware interfacing required whenever you want to work with this EEPROM device with controller. And now my consideration is as a 8051 master device, how to work with this EEPROM and what way. So I can connect this with controller because there is no availability on chip I2C availability of this 8051, but still I want to use this device as a master. Okay, and now this EEPROM is slave for me. So once you want to work with these 2 devices each other, just I want to use the memory locations of this 24C32 and how many locations are available inside for this device. So that should be 000H2 0FFH. So what data frame I can write for this EEPROM device? So what is meant by data frame here? So data frame means what way you people can do the operations. Like the data frame decides whether which operation you can perform with this EEPROM device. First, you people have to generate start condition, and already you know the start condition of this I2C protocol. So what is the start condition here? While SCL is high, you people have to make SDA low to high ones, and then you have to send this device address, which should be 7-bit, and the 8th bit should be read or write. So this read or write logic decides. If you are making logic 1 here, then you are performing read operation with the 24C32. Okay, and once you are applying logic 0 here, then you people are doing write operation with this EEPROM device. Okay, so and after this, just you have to check the acknowledgement, because after sending 8 8 bit of data from master to slave or slave to master, you people have to check this acknowledgement. And then, so once you observe this EEPROM device locations, so which are going to have the 16-bit size of address, right? So, but as a programmer, which is not possible to send 16-bit at a time, so you people have to divide this address as a two parts. So the first half is a lower byte address, and the next part should be higher byte address, which should be any location of this EEPROM. So now, if you want to access a particular memory locations of this EEPROM device, first you have to send higher byte address. So this should be 8-bit, right? So once you send this higher byte address, again the master will expect acknowledgement from the slave. Okay, so again you have to check this acknowledgement, and after once acknowledgement is success, then it will go for lower byte, and after that again it will expect this acknowledgement, and then you can send data. So whatever the operation you are expecting from this particular EEPROM location, whether it is a read operation or write operation, if it is a read operation, then you have to make this bit as 1, and if it is a write operation, make this bit as 0. Okay, so once if you want to do the continuous operations, you can continue, otherwise if you want to stop the communication, you can stop. So this is the simple data frame you have to write whenever you want to do the certain operations with this EEPROM device. So this EEPROM device which will perform the operations, the first one is start, and next it has to send device address along with read or write bit, and it has to check the acknowledgement, and it has to send higher byte address, and then you have to check the acknowledgement check, and lower byte address, and acknowledgement check, and data, and you can continue for next locations. Okay, so otherwise you can stop. So this is the simple data write operation with the EEPROM location. Okay, and whenever you are looking to read the particular location of EEPROM device, then simply make it this, so read or write bit as 1, then you people can go through this read operation. Thank you.